In the mid-60s, a small group of NASA engineers start work on a radical idea: to establish a permanent human presence in the lethal environment of space.
We were doing something that man had never done before.
A facility that has to operate 24/7.
A dream that will become the most expensive structure ever built, costing $100 billion.
That's a view you don't see every day.
The International Space Station. But to achieve this goal, America must change the course of history
Houston flight, Zug Moskva.
and work with a former enemy.
The Russians were there with their space station, and we were not.
Engineers must overcome seemingly impossible odds.
Let go, let go.
It was very intense. Adrenaline was running very high.
We had a spacecraft up there. We weren't going to give up on it.
And it was a perfect example of ingenuity in the moment.
This is the story of the unsung heroes who built the International Space Station.
Check is good.
August 2016. Over 400 kilometers above the Earth, NASA astronauts Jeff Williams and Kate Rubins are undertaking a critical spacewalk.
Okay, I'm in egress now, and then make these cables in egress position.
That sounds great, Jeff. Thanks.
They must fit a docking adapter that will allow both manned and unmanned spacecraft from different countries to visit the International Space Station.
Covers loose.
Okay, I will meet you at the back.
It will be the latest addition to an outpost in space that has been permanently occupied for 16 years. A 420-ton engineering marvel, the size of a football field. Traveling at almost 30,000 kilometers per hour, it orbits the Earth every 90 minutes.
Anyone here on Earth can look up at an appointed moment and see the International Space Station orbiting overhead. And that is a great testimony to the engineering prowess that went into it.
217 astronauts from 15 countries have lived on board. Many of them gazing back at the Earth from the extraordinary glass cupola.
I'm awed by the fact that we've had crews in orbit for all these years.
The term space station dates back to the 1920s. But it's Second World War rocket pioneer Wernher von Braun who was among those imagining an orbiting space station. Von Braun heads up a group of German rocket engineers brought to the US after World War II to work on America's early space program.
Dr. von Braun had the vision and the dream, even in the very earliest days of human spaceflight.
In 1952, he declares,
"Development of the space station is as inevitable as the rising sun."
Von Braun envisages a huge wheel over 70 meters wide, rotating slowly as it orbits the Earth. It's a vision that would be borrowed by movie maker Stanley Kubrick for his sci-fi classic 2001: A Space Odyssey. By the mid-60s, NASA is consumed with creating the rocket that will take men to the moon. Building a space station isn't a priority. But at NASA's Marshall Space Flight Center in Alabama, engineers, including George Hardy and Jim Splawn, are looking beyond the space race and making new plans.
Apollo, we learned to go to a destination in space and return. Now we wanted to learn about living in space and living for extended periods of time.
4, 3, 2, 1.
But the Apollo missions have been hugely expensive. And from 1966, NASA's budget is cut by 44%. Engineers are forced to use their ingenuity to design a space station on the cheap.
We just kept working on it until something came up that we could say, yeah, we think we're going to go do this, and it'd probably work.
Their groundbreaking idea is to transform the top section of a Saturn V rocket into a space station. Engineers take their proposal, named Skylab, to NASA, who give it the green light. But now they face uncharted territory.
Skylab gave you an opportunity to have a shirt-sleeve environment, to run experiments over a long period of time, see how well men can survive in space. They weren't too sure what the long-term effects would be until you experimented and found out.
First, they must bolt together their space station using the third stage of the Saturn V rocket. A telescope is attached to the old hydrogen storage tank, which is stripped out so humans can live inside. To make living in space more bearable, it will have a few home comforts, like a kitchen and a shower, along with a laboratory and life support systems. 2 massive solar panel arrays will provide power.
The mood around the engineering staffs was pure excitement.
This full-size backup at the Smithsonian's National Air and Space Museum is testament to the engineers' incredible ingenuity. But they now face the challenge of keeping a spacecraft in orbit for up to a decade.
Here you have a facility that has to operate 24/7. The maintainability and operability was the real challenge. We had never done that.
To maintain Skylab, astronauts will be required to undertake longer spacewalks than ever before.
This had never been pushed to the extreme of being able to stay out over just a very short period of time, like an hour or two.
To test those extremes, engineers must first replicate zero-gravity conditions on Earth. A small pit at Alabama's Marshall Space Flight Center is filled with water to try and simulate weightlessness.
One of the first things that we had to figure out is how can we compensate the flotation of a man in a pressure suit once he goes underwater. We decided that we could make a harness of lead weights to put on him. The weight counterbalances the volume of air around the body inside the pressure suit.
It works. Engineers make a man in a pressure suit neutrally buoyant underwater, neither rising nor sinking.
We decided that we should invite top management to watch a test. Go to the very top guy, and that was Dr. Werner von Braun. When he saw what we were doing, he said, yeah, he's good, keep going, keep going.
Von Braun gives the go-ahead to upscale the experiment into a $1 million project. 23 meters in diameter, 12 meters deep, and holding almost 6 million liters. It's officially called the Neutral Buoyancy Simulator, but it's nicknamed the Big Tank.
Why such a big tank? We had fabricated a full-scale mock-up of Skylab. We could get all of the ingredients there that we needed to have for the training of the flight crew.
Marshall's Neutral Buoyancy Simulator is a vital part of training astronauts to do DIY repairs on Skylab in zero gravity. But nobody could have imagined just how critical it would become. May the 14th, 1973. The countdown approaches for America's first space station, Skylab, packed into the top section of a Saturn V rocket. It's the first step to the ultimate goal of a permanent human presence in the most hostile environment known to man.
Ignition sequence has started. 5, 4, 3.
But just 63 seconds after launch, Skylab is in trouble.
We started seeing telemetry that there'd been a failure.
As the rocket cleared the tower and went up into the clouds, suddenly aerodynamic forces grabbed a piece of this micrometeoroid shield that protected the actual lab itself.
We had a big problem.
The micrometeoroid shield is mission critical as it wraps around Skylab's heart, its laboratory and crew quarters. Made from aluminium, it's primarily designed to protect astronauts from the impact of cosmic debris.
There was enough air trapped under it that expanded the vibration of the dynamic pressure, grabbed a hold of the top edge and ripped it off. It was like peeling an orange.
It was bleak. I felt the mission was lost.
The shield also performs a second critical function, doubling up as a sunshade. Exposed to the sun in space, blistering temperatures will soon make Skylab uninhabitable, destroying the mission.
As soon as we got on orbit, the temperature started going up. Temperatures got to 125, maybe even 130 degrees.
All the environmental control system, the life support system, the food, the electronics, communication systems, breathing systems.
Sooner rather than later, they needed to get some way to control the thermal conditions on the vehicle, or they would be lost in a number of days for human habitation.
The engineers are now in a race against time. Meanwhile, the crew, who were scheduled to launch the following day, are grounded. Tom Moser is part of the team's scramble to save the roasting space station.
We devised a parasol that could be unfurled, just like an umbrella.
The parasol will shield Skylab from the sun's extreme heat. But engineers must create it from scratch.
Designing the parasol to operate in zero gravity was a tricky operation. We could calculate some of the effects that it would have, but we haven't got the time that you would normally have when you're designing space hardware.
The team decides to use the same material that protects astronauts from the heat of the sun. But it's useless unless they figure out how to make a supporting structure.
It was like, what in the world do we have in our garages? Or what can we go to a store and buy that might help us do this?
Then inspiration strikes. One of the engineers thinks fishing rods might work. The plan is to fasten 4 of them together to create the engineering prototype.
We needed a quick answer, and I did think it was rather ingenious.
Fortunately, there's a tiny airlock right next to where the micrometeoroid shield would have been. The idea is for an astronaut to manually push the parasol outside through this airlock. 4 spring-loaded arms will then be extended to deploy the makeshift fabric sunshield, measuring approximately 7 meters by 7 meters. An inspired solution, if it works.
There was a huge time pressure to get that system designed and built and put up there.
The engineers managed to finish the Parasol in just 10 days.
It was very intense. Adrenaline was running very high, even though there was risk. If there was a chance that this would work, it needed to be tried.
May the 25th, 1973. The Skylab crew prepares for their delayed mission, which is now a daunting rescue operation. No one, least of all astronauts Pete Conrad, Joe Kerwin, and Paul Weitz, has any idea just how bad the damage to Skylab is, or if they can save it.
Your adrenaline is up. Your expectations are high. You really couldn't assess all the damage until you got there. There was an urgency in it.
Certain degree of apprehension. What's going to happen next?
Callie, the Skylab. We got her in daylight at 1.5 miles, 29 feet per second.
Roger, Pete, copy.
Closing in on the overheating space station, Pete Conrad reports the damage to the two main solar panels back to mission control.
Brief description is his suspected solar wing 2 is gone, completely off the bird.
Roger, copy.
The solar array, one of them is completely ripped off with trailing its little wires. The other one is held down, kind of pinioned by one of the straps of what's left of the micrometeoroid shield.
These images reveal the sun-blistered surface, exposed where the micrometeoroid shield peeled off. As the astronauts dock, they're faced with an unprecedented challenge. They must enter a spacecraft cooking at over 50 degrees Celsius to deploy an untried device in zero gravity. Failure will mean the loss of America's first space station. It's the moment of truth for the fishing rod-inspired Parasol.
So we are progressing slow but sure, and everything so far is working.
Engineering and flight teams in mission control hold their breath. The makeshift Parasol deploys without a problem.
We can see the ends of all the rods. It's completely free of anything. There's nothing hanging it up.
As the crew got the Parasol out, it was jubilation.
But the celebrations are short-lived. The station's survival also depends on deploying the one remaining solar panel.
The solar panels for the Skylab is the way that they have enough power to do any of the experiments, to keep everything working, to keep it cool. How they generate power for all of the equipment.
Pete Conrad and Joe Kerwin now face an extraordinarily demanding repair job. A critical spacewalk to free the stuck solar panel.
The only way to do that was to have two of the crew go out and do a spacewalk. Reach down to the base of where that strap is holding on to the solar array, cut it, and then pull the solar array out.
It's at this moment that Jim Splawn's big tank at Marshall comes into its own.
All the time that this was going on, we had air-to-ground communications. We were ready to help them in any way we could.
In the water, a backup crew mirror the astronauts' every move. Bob Crippen was part of the Skylab support team.
They had a device that was kind of like a long pole with a cutter on the end of it, like somebody might use to trim trees.
But can a design based on a $65 tree pruner really save a $2.5 billion space station? America's dream of a long-term human presence in space is on a knife edge. If Pete Conrad and Joe Kerwin can't free Skylab's one remaining large solar panel, it won't have enough power to survive. Everything rests on a single spacewalk.
Skylab, we're reading you loud and clear. Okay, Houston, we're out there. There looks like enough room to get the cutter.
So the solar array has been pinioned down by a small strap that's ripped off of the micrometeoroid shield.
Joe Kerwin was operating the device.
He was able to get into position and work the cutter.
Pete managed to put in an extra pressure on it.
Let go, let go!
He went flying away from the spacecraft.
The only thing preventing Pete Conrad spinning out into space is an 18-meter cord fixed to the airlock.
He was constrained by the umbilical, which held him in. You have to know Pete, he was saying like, wahoo, or something like that when he went out flying.
All right, let's got it.
That would have probably scared the dickens out of anybody else, but not Pete.
Pete Conrad said, "This is just like the water tank at Marshall, except it's a little bit deeper." So that was a good compliment. It's a good compliment.
The recovery of that mission was almost indescribable pride just to be a little part of it.
Two more crews will visit Skylab to carry out scientific and medical experiments, including the effects of weightlessness. The last manned mission leaves Skylab in 1974. 5 years later, it slowly re-enters the Earth's atmosphere, showering debris over the Australian outback.
There was a bit of sadness, I suppose, but a great sense of satisfaction on what had been accomplished.
The legacy of Skylab's engineers is a stepping stone to meet the next epic challenge in space. In 1984, President Reagan gives a State of the Union address that echoes John F. Kennedy's historic moonshot goal.
Tonight, I am directing NASA to develop a permanently manned space station and to do it within a decade.
This orbiting space station will be named Freedom. Canada, Japan, and the European Space Agency all sign up to the ambitious idea.
The goal is to provide a laboratory in space to do science and engineering research, to advance exploration.
The tragedy is just around the corner.
Challenger, go and throttle up. Challenger, go and throttle up.
As the world reels from the Challenger disaster, the American space program is put on hold. In contrast, their Cold War rivals are thriving. The Soviets have launched 7 Salyut space stations.
Having not landed on the moon, they focused their space program onto how to do these long missions in Earth orbit.
Just 2 weeks after Challenger, the Soviets launched the first module of their new space station, called Mir.
The Russians were there with their space station, and we were not.
But in 1989, the beginning of the fall of communism tips the Soviet space program into financial and political turmoil. America isn't faring much better. Space station Freedom is stuck at the design stage, thanks to holdups and budget cuts. NASA needs a radical rethink if they're to meet the goal of the president. In 1993, America does what for decades would have been unthinkable, asking its former Cold War enemy, Russia, to join forces on a newly named International Space Station, or ISS.
Since the launch of the Mir, the Soviets had a near permanent human presence in orbit, and that taught them a great deal. It was a vast resource that I don't think the Americans could have shied away from.
NASA are charged with designing the biggest ever structure to be assembled in space. Their solution is for a series of modular or segmented sections to be joined together. Rod Jones was a member of one of the ISS design teams.
What we learned from looking at the Mir was that if you put modularity into your design, you can extend and perpetuate the vehicle life for a much longer period of time. Modularity, it allows you to add things to the space station, take things away. It allows you to shift functionality around the space station.
But can these former enemies work together to create a new space station? June the 27th, 1995. Space Shuttle Atlantis lifts off to dock with Russian space station Mir.
Capture confirmed.
Capture is confirmed. Atlantis is now docked with the Russian space station.
It's the first of 9 missions that dock with Mir, allowing the two countries to pave the way for the International Space Station.
Mir became a destination for studying the engineering, the science, and human factors in human spaceflight.
With their old rivalries set aside, construction of the ISS modules gets underway. But their dream will be tested as both sides encounter a critical problem. The dawn of 1993. America's dream of a permanent human presence in space is under threat. With NASA strapped for cash, the only way of realizing their goal is to work with the Russians. But a major engineering challenge stands in the way.
Because we wanted to get the Russians on board the International Space Station program, we had to get them launching from their own launch sites, and those are up at about 52 degrees latitude.
The Russians launch all their rockets from Kazakhstan into a 52-degree orbital angle. And this is where the ISS will be assembled in space. But for the Americans, that presents a huge problem. The space shuttle usually launches from Cape Kennedy into a much lower orbital angle of around 30 degrees. The trouble is, to reach the greater 52-degree angle, the shuttle loses the boost it gets from the Earth's rotation that helps it into orbit. Bottom line, by carrying heavy ISS components, the shuttle doesn't have enough power to launch into the steeper angle.
To fly at those higher inclinations and carry up large payloads, you need more power.
Astronaut Mike Massimino is a veteran of 2 shuttle missions.
To get to that higher inclination requires more power, which means more fuel, but you can't add endless fuel because you're constrained by the size of your tank.
Engineers are forced to look at the only other option: make the shuttle lighter. They calculate it needs to lose 6 tons to give it enough power to lift ISS components. They shave nearly half by redesigning the shuttle's storage racks and even the crew seats. But they still need to lose another 3,150 kilograms. Myron Pessin was chief engineer for the shuttle's external tank.
The demands on us were extreme to get that 7,000 pounds.
So engineers come up with a radical solution. Make a new external tank from a revolutionary metal alloy called weldolite.
These aluminum lithium alloys were higher strength and lighter.
But weldolite is so new, it's barely beyond the development stage.
The material properties were still somewhat uncertain, but we all felt it was an acceptable risk to go forward with this because of the national need for it.
In February 1998, NASA takes delivery of the shuttle's new super lightweight external tank. Now assembly of the largest and most expensive structure in space can begin. But to succeed, the 15 different ISS modules must be docked precisely 400 kilometers above the Earth.
You had all these different pieces that needed to fit together in space. I thought to myself, there's no way that this stuff is all going to work. You can't get things to fit together, in your kitchen. How are we going to get this to work in space with different countries and different languages and rocket ships and all this other stuff? How's it going to work?
On November the 20th, the Russians take the first step.
Liftoff of the Proton rocket of the Zarya control module. The International Space Station is underway.
Zarya will provide the initial propulsion and power for the ISS, along with communication systems and docking ports for future modules. The pressure is now on the Americans. For the ISS to progress any further, the first US module, the Unity node, must be connected to Zarya in the lethal vacuum of space. December the 4th, 1998. Commander Robert Cabana and his crew prepare for an unprecedented mission.
We have main engine start. 4, 3, 2, 1. Liftoff of the Space Shuttle Endeavour with the first American element of the International Space Station, uniting our efforts in space.
2 days later, they rendezvous with Zarya, unload the Unity node, and inch it towards the Russian module.
Houston Endeavour, we have capture of Zarya.
The first stage of the ISS is born. Engineers have enabled two former enemies to build a permanent structure in space. These two modules are the first of what will grow into an enormous 15-module space station. 7 modules are delivered from the US, 5 by Russia, 2 by Japan, and 1 from Europe. But there are limits to what you can cram into a space shuttle. Transporting this giant jigsaw into space will be an epic challenge.
We made the modules as big as we could to fit them in the shuttle. The length of a module, it became like a bologna slice. How much can you afford to launch? And that's where you cut it off.
It takes 13 years, 37 shuttle flights, 160 spacewalks, and over 1,000 hours to construct the ISS in orbit. But building it is only half the battle. Allowing astronauts to be self-sufficient in space long-term creates a new raft of engineering challenges. This oxygen generation system provides 56% of the crew's breathable atmosphere. It works by pulling oxygen molecules out of water. But that's a monumentally expensive commodity to haul up over 400 kilometers to the ISS.
So this is almost a liter of water, and to get this into space, it's about $48,000 US.
As urine is 95% water, that makes astronaut pee a precious commodity. Jennifer Pruitt is part of the engineering team who have found an ingenious way to recycle urine on the ISS.
The overall goal is to take astronaut urine and pull the water out of it so we can have good, clean water for the astronauts to drink and to use on the space station.
On Earth, gravity makes extracting water from urine easy. Just boil off impurities and catch the clean water as it cools. But the way water behaves in zero gravity makes distilling it much more difficult.
One of the problems with trying to distill urine in space is that it's not going to have steam that rises like you would on Earth and be able to capture it.
This ingenious urine distillation assembly recycles astronauts' waste by creating artificial gravity.
This whole part is a centrifuge that'll spin. So the urine will be sprayed out along the back wall as it spins. The heavy, dense fluid will stick to the wall, and the lighter steam, as it evaporates out, will be sucked through the center, through that mesh, onto the next part of the system. So at the end, this is the good, clean urine distillate that you get. This is what will go on to the water processor assembly later on, and then will be the water that the astronauts will drink.
Since its installation on the ISS in 2008, 85% of the water in urine has been recycled in this way. Just hours after peeing, an astronaut can be drinking fresh water.
That's what's great about Space Station. This is something that had never been done before. It is so important for long-term humans into space.
Smart engineering like this has allowed the ISS to be permanently inhabited since the year 2000 by hundreds of astronauts. But lingering in orbit exposes space stations to a potentially catastrophic event: a high-speed impact. November 2016. The International Space Station celebrates 16 years of full-time habitation. Research carried out by ISS scientists is now helping to develop improved vaccines and advanced robotic surgical techniques for neurosurgeons on Earth. But this orbiting 420-ton structure is potentially at risk from a nightmare scenario.
There are just a couple things that you're really worried about when you're in space. They're always kind of like, all right, yeah. They're kind of living on edge. One is a fire, that would be bad. The other major problem is if you got hit, you would be in a life-threatening situation.
More than 100 million fragments of debris orbit our planet, traveling up to almost 30,000 kilometers per hour. At those speeds, even the tiniest piece can do serious damage. A fleck of paint gouged this crater into the windshield of a space shuttle. Damage to the ISS is unavoidable.
The International Space Station, it's getting hit. It's getting hit all the time. This is a major risk.
The ISS is protected by a layer of shielding. The frame is made of two thin plates of aluminium. The outer bumper layer causes debris to fragment on impact. Inside are 6 layers of ceramic fiber and Kevlar fabric stuffing. An inner layer of aluminium catches what's left of the energy of the impact. It's a huge advance in shield design since the single layer of aluminium used to protect Skylab. At the NASA Johnson Space Center, Dana Lear is using a high-pressure gas gun to test fire a particle at a potential new layer. If successful, it could be a new first line of defense for the ISS.
Okay. There's a small hole here in this outer layer we call the bumper shield. This is the first layer that's encountered by space debris. When it passes through that bumper, it actually tears the particle up. So let me take the outer bumper off. The second layer, it's not perforated, and you can see that particle has been broken up into small particulates.
There are 7 layers of this new material being tested, a metal alloy that's 90% iron.
If we go down to the last layer, you can see that we haven't penetrated any further into the shield, and certainly didn't penetrate down to the pressure wall. So this works really good.
Like Wernher von Braun 65 years ago, visionary engineers today see space stations as a stepping stone to explore distant worlds.
We learned very valuable lessons putting together the space station. That's going to be invaluable experience of how to engineer a big project on a place like Mars.
April the 8th, 2016. A SpaceX cargo rocket launches a revolutionary new piece of technology that could change the way we build space stations in the future.
And space engineering, because you're limited by the amount of weight you can take with you, you need to miniaturize as much as possible.
Good morning from Mission Control Houston. We bring you the installation of the Bigelow Expandable Activity Module, referred to as BEAM.
BEAM is a lightweight, flat-pack module, flown to the ISS in a small package, attached, and then expanded. Instead of heavy aluminium, BEAM is made from layers of insulating material covered with a silica fiber cloth. It also has an ingenious key feature.
During the expansion, we had rip-stitch straps that would essentially open up and allow the module to gradually expand. So it's pretty awesome.
ISP success, DC complete.
Houston copies.
If successful, BEAM will undergo a 2-year trial on board the ISS.
This is a stepping stone to see humans on Mars eventually.
The soaring achievement of the ISS owes an enormous debt to a previous generation of NASA engineers. Their ingenuity triumphed over seemingly insurmountable obstacles to save America's first space station.
We had some challenges, but we've managed to overcome them.
Some of NASA's greatest days.
You can look back now and you just got to grin a little bit because it was such a success story. And it's all about the people pulling together and getting the big job done.